With this video, we begin the study of particle kinetics. In other words, how motions are caused by forces acting on the objects. We need to first quickly review some fundamentals we learned in the statics course. Once again, I advise you to also review statics if you feel your fundamental knowledge is lacking. Let's first look at Newton's first law. For a particle subjected to forces, if the sum of the force vectors equals to 0, then the acceleration of the object, which equals to resultant force over the mass of the object, is also 0. With no acceleration, the object will either be at rest or moving at a constant velocity with no direction change either, and this is called the state of equilibrium. This was the focus of the statics course. But if the forces acting on the object has a non-zero resultant force, then the resultant force equals to the mass of the object times acceleration. This is known as the equation of motion. It can be represented by a kinetic diagram, and the vector ma is called the inertia force, since it is, quote, equivalent, unquote, to a force vector. So it can be rewritten this way to show that acceleration is the result of unbalanced force. And from this formula, you should also appreciate how mass of the object being on the denominator serves as the inertia to motion. Mass resists change in motion of the object. So, with a non-zero acceleration, the object is doing accelerated motion, and the acceleration is in the same direction of the resultant force. This is Newton's second law, the most fundamental law in our class of dynamics. And just quickly, Newton's third law of action and reaction, which states that the forces are always exerted by a pair of objects on each other, and the forces between them are equal, collinear, and opposite. Newton's law of gravitation. Gravitational attraction force exists between any two objects with mass, and the magnitude is calculated by this equation: g, the universal constant of gravitation, multiplied by the mass of object 1, the mass of object 2, and then divided by their distance to the second power. And as you can see, the reason why we don't feel this force just between any two bodies is because this constant g is very small, on the order of 10 to the negative 12th power. But we do feel the gravitational force exerted by the Earth to us. We follow the same equation for gravitational force, but substitute in the constants of the Earth's radius in mass and collect all constants to be one constant, small g, and then we get this equation that we are so familiar with, that the weight of an object equals to its mass times g, with g being 9.81 meter per second squared in SI unit system, or 32.2 feet per second squared in US customary system. Note that since the radius of the Earth does vary from location to location, this g constant is only an approximation, but it is a good enough approximation in most cases. So here is the general procedure for solving particle kinetic problems using equation of motion. First, just like solving problems in the course of statics, we need to set up a convenient inertial coordinate system. It could be rectangular, normal, tangential, or cylindrical, depending on different situations. However, the coordinate system must be inertial, which means that it itself must be in equilibrium. Again, according to Newton's first law, this means that the coordinate system is either fixed, not moving, or translating at the same speed along the same direction. In our class, normally this inertial coordinate system is chosen to be fixed on Earth. We want to make this very clear because we might use translating or rotating coordinate systems as well to study relative motions. Then we draw the free body diagram of the object. Again, please review statics if needed to refresh your memory on how to correctly draw the free body diagram. On the free body diagram, you need to include all external forces applied to the particle, and resolve your forces into components according to the coordinate system you set up. Then, draw the kinetic diagram showing the particle's inertia force, also resolved into appropriate components. Then, write the equation of motion in a scalar form along each axis of your coordinate system. Identify the unknowns and solve for the unknowns. Sometimes you might need to apply kinematics equations, so don't forget the 3 basic kinematic equations. Again, the most basic coordinate system is the rectangular coordinate system. For a 3D problem set up in the rectangular coordinate system, from one particle free body diagram, the vector form of the equation of motion can be written as 3 scalar equations of motions along the x, y, and z axes respectively. So keep in mind that based on one free body diagram, you can solve only up to 3 scalar unknowns. For a 2D problem, the equation of motion is written into 2 scalar equations, enabling you to solve for only 2 scalar unknowns. It is always important to analyze first if you have enough independent equations to solve your unknowns, rather than jumping at the problem right away. The equation of motion can also be applied to a system of particles. When you draw the free body diagram of a system, make sure you only include forces that are external to this entire system. Do not include any internal forces between the objects. Then the equation of motion can be written as the total external forces equal to the summation of mi being the mass of each individual element in the system, and ai is its acceleration. And this can be summarized into m times ag, with m being the total mass of the system, and ag is the acceleration of a point located at the mass center of the system. Let's look at this example. There are 3 toy cars. The mass of each is given, and they are connected together, and they are being pulled by a horizontal force with a magnitude of 3.5 Newton. We need to determine the acceleration of the cars and the force between car A and car B. We can neglect friction. To solve the first part of the problem, we need to draw the free body diagram of this entire car set as one system. Therefore, we need to include all the external forces acting on this system. We have the applied force 3.5 Newton. We also have the total weight force as well as the total support force. And this completes the free body diagram for the system. Therefore, we can draw the corresponding kinetic diagram showing the horizontal inertia force, which equals to the total mass times acceleration. Because there is no motion along the vertical direction, there is no acceleration along the vertical direction. Now, before we write the equation of motion, we need to set up our coordinate system. We choose the positive x direction to be conveniently pointing to the left. Therefore, the resultant force along the positive x direction, which is simply the applied force 3.5 Newton, and this equals to the total mass times the acceleration along the x direction. We substitute in all the numbers, and we can calculate ax to be 10 meters per second squared, also pointing to the left. And this is the answer to the first part of this problem. For the second part of this problem, to solve for the force between car A and car B, we can no longer treat the entire toy car set as one system, because if that's the case, then the force between car A and car B is internal and cannot be solved. Therefore, we need to draw the free body diagram of car A only. This way, the force between car A and B is now exposed to be an external force. We also need to include the weight force and support force, and this completes the free body diagram. And then we write the equation of motion on car A only. The resultant force acting in the positive x direction equals to F minus FAB, and that equals to the mass of car A multiplied by the acceleration along the x direction, which we solved for during the previous step. So we substitute in the known values and solve for FAB to be 2 Newton, and that completes this problem.